There we go. And let's maybe see where we left off last time. So that's what we were just talking about before I started the live stream. Remember, your quiz is September 30th. And last time we ended with this problem. So hopefully you had a chance to go through all that. And that's pretty crazy. They're not always going to have parts A through M. That's insane. But yeah. So I thought we'd start off again and see, let's just try a problem and see what we remember from last time because it's been a while. And so let's start with question 2.14. And our goal, again, is to try and use the problem-solving strategy. Read, draw, label, list your knowns, list your equations, et cetera, et cetera, et cetera. And so there's a couple of little tricks in this problem that are worth seeing and reinforcing. We talked about them already. I think you have a chance of getting them, but expect to make a few mistakes here and there. So everybody, why don't you try and set up this problem while I also try and set up this problem on my whiteboard, and I'll adjust the screen later. So again, 2.14. At any time, throw a question in the chat for Jay. So yeah, all right, she's there waiting for you if you have a question. 2.14, everybody. All right. And so we're probably looking at parts A and B. So let's go ahead and look at this one. And let's see. Does anybody feel brave and maybe want to unmute? Let's look at part A together while it's all on screen, and then the rest of it, we can take this off the screen. So before I take this off the screen, let's look at this equation. According to the coordinate system shown, which of the following equations is incorrect? Now, you probably know, well, let's see. I don't know. What do you think? Anybody have any thoughts? It's Monday. I know it's awkward. Somebody try to be brave and just go for it.
Is it the third one?
Let's take a look. So right here, this one is correct, actually. I appreciate the bravery there. So if you move this over, I don't know if you agree, that's going to become negative, and that actually is delta y. So delta y is equal to v initial y times time. So that one ends up being correct.
Oh, the first one.
Ah.
Yeah.
That one is clearly wrong because you see the minus. And so let me finish writing this. Very good. Excellent job. I don't know who that was, but thank you. All right. The idea is you can see this is wrong. Now, the idea here, if you look over in this coordinate system, this is the y direction. G is a positive number. We see that a sub y is not G. It's negative the magnitude. The negative comes from this arrowhead right here. So that's one of the things I wanted to focus on here. A lot of times people will accidentally write down this because they're thinking this middle one. But so just be aware here. I want you to know the difference between a sub y, which is the acceleration in the y direction, which should include the plus minus signs, and g, which is just the magnitude, which is always positive. So that was the point of a, just to kind of reinforce the magnitude is g. That's a positive number. And that's why you have to manually put in the minus sign here from the arrowhead. All right. Any questions about that before we go on? That's just a common thing that students screw up. So I just wanted to bring that up. I'm going to assume we're all good on that now. So now this is another part. I just want to be clear here. We want the time to impact the ground. That's where we're going next. Okay. So let's take a look at the whiteboard here. Time to impact the ground. So this is what I drew. You might have drawn something different. Always good to have the problem number. That's my attempt to draw a little hammer. I've got my coordinate system, the magnitude, the direction. I've written down some key assumptions. We've been told the size of the hammer is negligible. So this is my way of saying that. The size of the hammer is much, much less than h, which basically means, let's say this building is 10 meters tall. This is maybe like 20 centimeters. Out of 10 meters, what's 20 centimeters? Who cares? It's not important. So especially because we're also ignoring air resistance, and we know in the real world that that's going to matter. So we're making some assumptions here, and I'm listing them because I think that's important to kind of make clear, hey, this is not going to be a perfect answer. It's a guess. It's an approximation. It's a good idea. Or it's a good estimate of what this thing might do, but it's not going to be perfect because of these things we've neglected. All right. So we were asked to find time to impact. Now, a lot of students, when they take a physics class, really get hung up on these words. And so I want to spend just a second on this. To be clear, let's say we're talking about this marker dropping and hitting there. All right. So again, we're going to have this marker drop and it smashes into there. Now, obviously, a few seconds after it drops and smashes, we see this marker is not doing anything anymore. For a physicist, when I say time to impact, I usually mean time to just before impact, when it's just above there, it just hasn't hit yet. Because at that instant, it's still moving downwards. Once it makes contact with the ground, the problem gets very tricky. It's not in free fall anymore. When it's falling, it's in free fall because gravity is the only force. As soon as it touches the ground, that's a different problem because it's not in free fall anymore. So just be aware, usually for a physicist, time to impact implies time to the nanosecond before impact, just before it hits, whatever. Let's get our list of crap. All right. Oh, well, time to impact means I don't know this. Got it. Somebody else, I don't know who that was last time, but somebody different. What do you think delta y is? We dropped the hammer. What do you think delta y is according to this picture? And the more you speak up, usually the better you do. Even if you feel like you're like being stupid or something, trust me. If you make mistakes in class, that's fewer mistakes outside. So feel brave. Speak up.
It's going to be H.
Close. It's not H. What does delta y mean? Do you remember what it means in this context? Does it mean distance, position, or displacement? Do you remember? It's okay. It's been a week. This means vertical displacement. Remember what is implied with this? What's implied on this delta y here that we haven't been writing?
A subscript. I can't remember.
A j hat. Sorry about that. So if I say that, does it change? Is delta y in the positive or negative j hat?
It's going to be negative.
Exactly. And this is why we're doing this problem as a team here, because most students, the distance you fall is h. You were absolutely right. But this means vertical displacement with a p. And so it is not h. The answer here is negative h. And that's the most commonly missed minus sign. So now that you spoke up, you probably won't miss that again. And thank you for doing that. I don't know who that was either. So good job. It's a good day to speak up because I can't see anybody talking because of the viewpoint I have on Zoom. So you're good to go, anybody. All right. Thank you for speaking up. How about V initial Y? Anybody else? Somebody new?
Is it 0?
Why do you think it's 0? What gave you that thought?
Because the hammer starts off at the top of the building, right? And then Thor drops it.
Drops it. Drop. Because drop is different than throw. I would think drop means 0. Right? We don't think of when you drop something, that's different than throwing it downwards. So that was good. That word drop somewhere in there makes me think, okay, release from rest. So we see that in physics, dropping, release from rest are two tricks that physicists use in the problem statement to get a 0 into the problem for you. Excellent job. V final Y, do we know what that is or not? I have no idea. I haven't read it. I'm talking to you. So what do you think? Somebody else? All I'm asking is, do you think this is a known quantity or a unknown quantity right now?
It's an unknown?
Yeah, I don't see anything. I didn't see anything about that telling us. So I'm going to say I don't know what this is. Okay. And then AY, somebody else. What do you think AY is?
It's gravity.
Okay. Be careful. Gravity is a force. AY would be related to that. Gravity is what causes AY. But yeah, that's just me being a physics teacher.
Okay.
What were you
G?
going to say?
No, not G.
Did you say G?
Yeah.
And that's not right either. But you're very close. What did you miss?
Sine theta.
Minus sign, right? G is the size of it.
Minus sign.
Yeah, because this one's down and this one's up. So we see it should be negative G right there. And that's the reason I want to do this problem. Because for the most part, the rest of this problem is pretty easy now. But if you miss one of these minus signs, you're toast. All right? Because usually now, and this particular problem is actually one of the easier ones. So you could actually miss both minus signs and perhaps get the answer right. And that's why students have trouble. They could screw up on the easy ones and somehow still get the answer right by luck. But just be aware. Always think about this as having J hat on it, okay? All of these have a J hat. And
so when we plug that into the equation, do we put like negative G, or is the negative
take a
already
look.
calculated like because there's a minus sign, right? Usually.
We're doing that next.
Okay.
So he's already jumping ahead. I'm going to write my equations here. Delta Y equals V initial Y times T plus 1/2 A sub Y T squared. V final Y okay. Are you guys able to see that okay? I don't know. I'll scoot it just a little bit. I think I can get it a little bit bigger. Hopefully that's a little bit more clear. Sorry. I don't know what to do about this glare all the time. I just don't know why. I guess the computer, right? You could see the computer's emitting light onto the whiteboard there. So whatever. I'm doing the best I can here. All right. All right. So let's take a look. What's the first thing we should do before we get all crazy here? Plug in the
0?
Yeah. Do you agree that why don't we just plug in the 0? And I'm going to get lazy just so I have some room. Doesn't that make these equations look a lot prettier to deal with? Just drop that out. So now I'm just going to scoot that over so I have a little bit more space, okay? Nice job, whoever that was. Thank you. All right. And now I forget who that was earlier, but we could actually plug in this stuff. So let's start plugging in the letters now. And so to do that, I'm going to get a minus h equals 1/2 negative g t squared. And I just want to point out, if we are consistent and follow the coordinate system, this minus sign will cancel out that minus sign and time will end up being a positive number. And that's what people get kind of weirded out. They're like, wait a minute, if you do these right, it's a check on your answers. You know that minus signs should not appear under a square root. Now I'm kind of skipping ahead here, but I could see how I could flip this stuff around and solve for t, and it would be the square root of something. And I could see that the minus signs drop out. H is a positive number. G is always positive. So I end up being good to go. H is a height. A height of a building is a positive quantity. G is a magnitude of acceleration due to gravity near Earth's surface, blah, blah, blah. So far, so good. Whoever asked that question ago when we talked about plugging in, did I address it or not?
Yeah, no, I was just wondering more like relating to the formula that you pointed out at the top with gravity. I mean,
This
no,
one?
sorry, for question A with gravity.
Oh, right.
Because you know how I had a minus sign already because there's gravity on that side, and that's what you were saying because gravity.
Yeah. So that very first, so let me make sure let me get that back up. So I think what you're saying is, notice that if you had done this, you would have put in 2 minus signs, and then we'd have a minus sign under the square root and be wrong. So this can't be right. The idea is if you plug in, so AY would become negative G. And if you do that, you would get this equation right here with the G and the negative.
Yeah, but
we don't want to,
so
we don't want to stick in.
So for the middle one, would you plug in negative G and then it'd be positive? So
no, G is always positive.
Okay.
So this is correct as written. This is correct as written. And remember that G is always 9.8 positive.
Okay.
And so either one, and the idea is, this is hard for students at first because they want to think gravity's negative because it pulls me down. You're right, but we've already accounted for that with this arrowhead versus this arrowhead. The comparison of the two arrowheads is what gives me this, and G is always positive, always positive. All right. Is that better?
Yeah, that's better.
Right on. Okay. And so at this point, I just want to show you another equation down here. Look at this V final Y, right? In this case, what if we plug in these numbers? This would be a negative H. This would be a negative G. And once again, notice that the final velocity squared, which should be a positive number, will end up being positive as long as you follow the rules that I'm telling you here, right? As long as you pay attention to the difference between G being a magnitude and AY being the acceleration, which can have the signs. The minus signs cancel. We get a positive number under that square root. So let's read the question and see. This is always the part where we did all the hard work. Now let's read what we're supposed to get. And we're supposed to get time. Do you agree we can get that from this equation really quickly? So I think if you solve that one, well, I'm running out of room, so let's just show it in the solutions, all right? What was this, 2.14, I think? So notice you end up getting this right here. Okay, so there's the answer. And then look at the checks, the units, all good. Let's see, we have meters over meters per second squared. Well, if I want to check those units, let's get a second squared over meters on both sides. on the top and the bottom, excuse me. So rather than try and do it in my head, I see the second squareds drop on the bottom, the meters drop, the meter drops on the top, and I get the square root of this, which is seconds. That's the unit of time. Units check. And now think about this. If H becomes a bigger number, you're dropping it from a taller building. Shouldn't it take longer? T increases if you use a taller building. That seems reasonable. What if you go to the moon? G is a smaller number on the moon because it's a different astronomical body, right? Or Jupiter. So if you go to a different planet, G changes. If you go to the moon where there's less gravitational force, you get less gravitational acceleration. G becomes smaller, the time becomes longer. Those are the kinds of things that you could do if you solve problems algebraically to check your work. You can't do that if you plug in numbers right away. All right, so there's a bunch of stuff there. Let's call that good for a second. Any questions while I still have that up? And you've got it too, right? So again, you could work ahead if I'm too slow for you guys or whatever. I don't know what you guys are doing here. So, all right. So out of all that, I'm just going to write down what we found here. I've already lost it. What was it? T is... what was it? 2H over G? I think that's what it was, right? Was that what we found? Sorry, I got to look it up again really quick.
That's correct.
Oh, thanks. Okay. All right. So now I've got that, and now I have a little bit more room to work with these ones here. So I'm going to scoot them a little higher on the board. So we said that V final Y should equal A sub YT. Or we also said V final Y squared is equal to 2 A sub Y delta Y. That's what we had left. And okay. And we even went further. We could stick in what we found here. I don't know if you remember, this had a minus sign and that had a minus sign. So this ends up being just 2G H with the minus signs canceling. So again, whoops, sorry. Gosh, that glare is killing me, man. Whatever. There we go. That's a little better today or something. All right. So again, right here, the minus sign canceled this minus sign, and that's why there's no minus signs written there. Okay. Now, in this case, what is V final Y? I guess I'm working on this one. I might as well finish it on this one, right? So what is V final Y? How would I get that, everybody? Take the square root, right? So what's wrong with what I just did? Why is this not the answer?
Did you forget the plus and minus?
Yeah. In this case, in any physics problem, when you take the square root, you'd better think about the plus minus. Why is the minus sign correct and not the plus sign in this problem?
The velocity is going down, so it's negative, right?
Yeah. At the end of the problem, right, isn't the hammer moving down? So think, this is where you're supposed to know, oh yeah, velocity final in the Y has an implied J hat on it. So you're supposed to say, oh yeah, it's either plus or minus. In this particular problem, at the end of the problem, it's going downwards. So the minus sign makes sense. So that's why this is correct. You need that minus sign. Here's another way. How could we check our answer? This is the third equation that we haven't used yet. We can now use this to double check our other two answers and make sure they make sense. Well, we have said over here, we expect this to be negative square root of 2GH, right? Well, let's take a look. V final Y is equal to negative G times the time up here, which was this crap. Two H over G. And now all I'm going to do is get, I'm just going to bring this inside, but to bring this inside, it's going to be a G squared, right? So I brought this into there. To bring it inside the square root, I have to square it. And lo and behold, this cancels one of those, and we get back the same answer. So that's what the third equation is really nice for, if you ever have time for it, which is rare during a quiz. But, you know, if you finish early on a quiz and if you get really fast at this, you could actually use the third kinematics equation to check your work. So far, so good. I'm going to go to the, yeah. Just let me know how you're doing, people. Just thumbs up, thumbs down, throw anything you want in the chat. Any questions? This would be a good time to pause before we go on to graphing. Appreciate it.
I have a quick question.
Yeah, do it.
So once we find like one of the missing, I don't want to call it factors, but like
One
the
of the
V final Y
unknowns?
or the time, yeah, the unknowns.
Mhm.
So basically we use the next problem to solve and find. Is that basically how it's supposed to go?
A lot of times you're right. And so I would say it like this. In a physics problem, you have to do so much work to get the first thing, right? You got to draw, you got to write, you got to reread, you got to do this, you got to write out some equations. And then once you find the first thing, after that, it's usually negligible effort to get the second, third, or fourth thing, whatever you need to do in a physics problem. Now, in these simple problems, there's usually only two things. So a lot of times in a typical course, a test question would be part A, get this, part B, get that, or switch the order. And so you're like, oh, okay. Now in a Canvas quiz, I can't ask multi-part questions. And so you might just get one of the things on a Canvas quiz where I just say, get the time or get the velocity, but not both. Is that good? Or no? No, or what? Oh, I didn't address it. Okay.
I think when I was trying to do the homework, I would find the answer and then use like the same equation to then move on to the next. But it seemed like you used one and then that equation was good, then you move to a next. Is that typically how it goes?
Oh, I see. Yeah, a lot of times for me, I like to do it that way. So,
Okay.
because I kind of think of it like you've got two things that you don't know. That means the only way you could really do it is to use two different equations, sort of like in algebra. They would say two equations, two unknowns all the time. That's what
Okay.
this is. And so for us in a physics class at this level right now, a lot of times one of the equations, like this one right here, allows me to get V final Y without having to rely on my other answer. This one allows, this one up here allowed me to get time without having to worry about V final Y. Why did I do that? Let's say I screwed one of them up. Well, if I screwed up V final Y, I still have a chance for getting points for this one because I didn't use any. You see what I'm saying?
Oh, that makes
So
a
by
lot of sense.
using two different
Okay.
equations, the odds of one mistake propagating through the whole problem go down.
Okay.
Now, and that's
makes a lot of sense.
really the only reason I do it that way. But like I said, you could have just gotten this one and plugged it in here and been done. But since you had the third equation, then you could use the third equation to check. And you could always use that
think-
if you have time.
Yeah, if time was an actual like number, I probably would have just plugged it in. But okay, I
Yeah,
completely get
exactly.
what you're saying.
Yeah, I'm
Okay.
with you there. And I would just use
Thank
this as a
you.
check. Yeah.
Right. Makes sense. Thank you, sir.
Yep. And it's funny, I generally reach for the delta x equation and the V final equation, or sorry, the V squared equation first. I don't know why. This one tends to be really good for problems with max height. And the other one is just kind of my favorite. So that's probably why I do that. I don't know. It's just the first one in the list and I ended up using it a lot. So there's no rules though. Anything that works, works. All right. Yeah. Where were we? Let's see what we didn't answer on that question. Okay. Oh, okay. So notice here, let's make sure we cover these words here right now. This is kind of the physicsy part rather than just the algebra part. So look at part C. If I say final velocity, a lot of times students say it's 0 because it hits the ground and it stops moving. Remember what I said earlier. I mean impact velocity, that's just before it reaches the ground. Okay, so be aware if you see impact velocity, that's the velocity as it makes impact just before it hits, blah, blah, blah. We do not mean when it hits the ground, it stops eventually, that's a true statement, but that doesn't help us with our math. We don't know how long it takes to bounce around and kind of stop. Okay. How about this one? Somebody, is impact velocity the same thing as impact speed? What do you think? And if not, how are they different? Go ahead and take a stab at it if you're feeling brave, right? I'm here to help you. This is a tricky part.
No, it's not the same.
So why are they not exactly the same thing?
Because wouldn't like velocity tell you like where or like what direction like the impact is made?
Right. And then what about speed?
Speed just tells you how fast it is.
Exactly. So how do they relate?
Because speed is a part of velocity.
It's the magnitude. So if you have impact velocity, like right here, whoops, sorry. Good job. You did a great job. So here it is, right? The impact velocity has to include the plus minus sign. Impact speed would be just the magnitude of that, which is the size of that. So watch out for a question on a quiz. This is right? You imagine you do all this work on a quiz and you get the final velocity and then you read it carefully and I asked for impact speed. That means you'd have to get rid of the minus sign because I asked for the magnitude of it. Or what if you did all this work and got the final speed, but you weren't paying attention and I asked for velocity? So I don't know what you're going to do. You've got to get this down. Make sure you read the words carefully. Did I ask for speed? Did I ask for distance or velocity or displacement? You really need to be looking out for velocity, speed, displacement, and the words in the problem. Magnitude versus just a vector, things like that. Okay. That was good. And then, okay. So I want you to do these two at home. All right. Parts E and F at home after class here. And I just want to be very clear. This is all about the words. Okay. And you have to learn how to read a physics problem carefully, or you'll just miss stupid points all the time. How do I know? Because I missed them when I was your age. Everybody screws these up. So screw them up now in the homework so you don't screw them up on quiz day. Look at this one. Determine the distance traveled. Distance. I asked for a distance, not a displacement. And it's speed. See how I'm mixing it up on you? I'm asking for its speed after the first half of the total travel time. In theory, you should be able to take this time, divide it by 2, and just figure out those things and make sure you think about the plus minus signs, okay? Next, look at this. What about the time to travel half the distance? That's a totally different thing. It looks similar, and the speed after the first half the distance. So that is after you've fallen halfway. And what we learn in this problem are the following. All right. So if I could show you right here, speed and velocity are not the same thing. Half the distance and half the time are not the same thing. And you could check your results with the simulation, and I could show you that simulation here in a sec. All right. So that's that question. I'm going to get that sim ready. All right. So just be aware. I mean, this is a great problem to go through thoroughly. So 2.13 and 2.14, man, make sure you get those exactly perfect. If you don't understand anything in the solutions, you got to talk to me. And after that, these get a little easier. So let me see if I have a couple of things for you. Where did that go? I want to make sure I have that one. So I mentioned this last time. So if you want to see about gravity and free fall, that's a pretty fun video. I don't have time to show you a whole 4-minute clip, but if you want to save that for after class, or if my lecture is really that boring, just hit mute and watch it. All right. And then let me do this other one. So if you search for PhET projectile motion, you'll get this. Whoops, let me clear all my crap off of here. All right. And I guess I could copy this for you too. It's kind of a fun little thing to play around with. So the idea here is this. I could take something like this, and now what I'm going to do, I'm going to set the initial speed to 0, okay? So again, what I've done is, all right, hold on. It looks like I'm going to shoot this thing down, but because I've got an initial speed of 0 down here, down at the bottom, I don't know if you could see that. This is the problem that we just did, okay? It's drop the rock, all right? And so when I run this thing, oops, I'm still on that annotate mode. So I'm going to hit the button, and it's going to drop the rock. Oh, let's see. What do we feel like dropping today? How about, let's drop a Buick or something, okay? All right. And I want to notice here's air resistance. We've turned that off. So this is no air resistance. And all right, that's great. And so let's go ahead and run this thing. So there's our Buick falling down. And then I don't know if we could show you this. All right. So, oh gosh, Zoom's clogging up my brain here. All right. So right at the top, we're at 15 meters. Notice the time is 0 seconds. Let's get all the way down here, pretty close to the bottom. It looks like it takes about 1.75 seconds to fall all the way down. Now, in this case, 1.75 divided by 2, that's about 0.9. So if I could, remember, this is right down here at impact. This is about 1.8 seconds, not quite. But look at the dramatic difference here. This is half the time, and this is half the time. And it turns out, if you do the math, which I told you to do, 1/4 of that 15 meters, you only fall 1/4 of it during that first 0.9 seconds. And it turns out 3/4 of it happens after that. And you could think about this. Your average speed for the first part is really slow. So you take more time when you're moving slow. And then down here, you're moving really fast. So you could actually cover more distance in the same amount of time. You've already sped up some. So that problem kind of walks you through all that. If you want to play around with this one, there you've got the simulation and you could do all these things. And so you could get a feeling for this. Notice this. Let's see, half the distance would be, whoops, come on. So half the distance would be somewhere in between here. So let's just go right there. And notice you take most of the time to cover the first half the distance. Most of the time to cover the first half the distance. And you could read the problem. I think it ends up being something related to a square root of 2 somehow. There's a square root in there and you get a 2. So I'll let you do the math on that. So that was all I wanted to point on that. Any questions while I have the simulation up? Feel free to hit the chat or all right. Okay. And so let me see where I want to go next here. Hopefully this is starting to like tie it together a little bit. And at this point, you could do all of the problems up to 2.24. Now, I don't know if all of those are required. And it looks like, yeah, they are. So up to, and I know this is crazy. It's a lot of problems, but the idea is the more of them you do, this just will not be an issue for you in the next class. And so a lot of my students like really hate this part of 110 because there's a lot of problems to do. But then when they get into 161, which is worth 5 points on your GPA, right? They're sitting there and you get, I think it's 5, maybe it's only 4, but it's a bigger class anyways. That at least the first 6 weeks of that class feel not so intense. That leads to its own set of problems, but whatever. So let me make sure I said the right number there. Sorry. Yeah. Okay. So up to 2.24 are totally doable for you now. And again, the more you do now, the easier Physics 161 will be during those first 6 weeks when you're really getting punched in the face in lab. Okay. So yeah, definitely the harder you could work on this, the better. Next up, we're going to go to, yeah, right. It gets intense. Plus we're almost certainly going to do ERT in the spring, which means you're going to almost certainly be doing a lot of coding. And a lot of you are not any good at coding. So it's going to take you a long time, those first 3 or 4 weeks, to deal with the coding. So the better job you do at these questions now, the more time you could spend surviving the coding portion of the class. It takes at least 3 weeks for people that have never coded to kind of get their feet under them. And you could ask Jay more about that too. She had to do that as well. But let's go to page 31 now. Okay. So where is that? And the coding is actually, it's kind of exciting. You just have to have a positive attitude about it. I personally hate coding. I quit coding for like 20 years, right? And then I came back to it. It's not nearly as bad as I remembered when I was a kid. So yeah, so don't be too scared about that. Let's worry about that later. We're going to talk about this. This is page 31, graphs, plots, charts of motion. So I need to get a simulation set up. So you guys all get page 31 open in your workbook and start reading that while I get this next simulation open, okay? So you guys are reading page 31. I think the Java version is better here. Maybe. There it goes. So you remember this that we looked at before. I'm going to put it up on steroids now so we can see these graphs. All right. And let's get this out of here. I can't see with the zoom crap. Okay. And so I'm going to pick, I think last time, I don't remember what we did, but let's say we had -4. Let's say your initial velocity is 6. And let's say your acceleration is -2. And then I'm not sure if this thing's going to hit the wall. So I'll take the walls out and I'm going to run this one. The idea is I want you to understand this. As this guy's going around, we see he's moving forwards, slowing down, stop. And then he turns around, and then he goes backwards. And then maybe I'll just stop this right here. Wow, I actually hit it at 10. All right, that's pretty cool. I actually hit it right. So now you can't really see this one very well. So I'm going to blow this up a little bit. Oh, let's blow up the time a bit. All right, that's pretty good. There. All right, and so we want to understand every single part of these graphs, all and how they relate to each other. That is our goal in this section of the course. The explanation for them, the shortcut, is right here. So now that you have this on your screen, the idea is this. To be clear, the name of these graphs are going to be position versus time, not distance, position. Velocity versus time, not speed, and acceleration as opposed to acceleration magnitude. Again, I do want to stress Position is a vector. You could get positive or negative positions in the I-hat, right? Velocity could be plus or minus in the I-hat. Similarly, acceleration could be a positive or negative number in the I-hat. We're not going to write the I-hat, but an I-hat is implied. Obviously, if we're doing things vertically, you'd have a J-hat implied, okay? So we're not writing on all of these things, okay? Now, let's keep going down here. The most important two that I want you to understand at first are the XT and the VT. And I believe on your quizzes, you're going to get XTs and VTs, and it's just going to be chosen at random. So some of you are going to get XT graphs, some of you are going to get VT graphs, but there's going to be multiple graphing questions. So the statistical odds indicate you're going to get graphs of both types. So you really need to understand this and this, to a lesser extent, the AT. Okay, so you really have to know XT and VT extremely well. I cannot stress that enough. I expect you to have all this stuff not only memorized, but actually understand it and know how to use it. And the questions that I'm going to ask you in the workbook and on the quizzes will force you to demonstrate your understanding. It's not like I could just say, hey, what does this mean? And you answer something that's, you just memorize an answer. You have to know how to use this stuff. Okay, so now in these graphs, this is something right away that pisses people off. X is on the y-axis. Look at this. Vertical position is going to be X. Horizontal is going to be time. Let me show you that. Let's go back to those graphs we just made. Where was it? Right here. Okay, so to be clear, where's my annotation? There it is. Look at this. The horizontal axis is seconds down here at the bottom. This is time down here at the bottom, seconds. So notice this would be, what is this? This right here is 7 seconds. T is on the horizontal axis. And this would be 10 meters, right? And look at this. At the very end right here, -10, that's the final position. It's about -10. You can see that's pretty close. All right. That's cool. So that's, just be aware of that. Let's go back to that other one. And let me actually pause for a second. Is this helping? Or is this getting you somewhere? Or is this a waste of your time? All right. Let's keep doing it then. Hit this button here. Okay. Okay, thanks. Okay. All right. So now, oh, wait, let's go back to this one here. So watch out. I can't stress this enough. This silly little implied I-hat that I keep hammering on, right? If I don't do that on test day, you're going to make that mistake. So I'd rather be boring and repeat myself a lot and lock that in. Okay. Look at this. Vertical intercept of the XT plot means initial position. Let's go look at that. Where were we? We were right here. So I'm going to rewind this thing. I'm going to hit the playback. And now it's not perfect. You see there's a numerical artifact here. It doesn't start exactly at -4. So again, we're supposed to be starting at -4. And that's just because to do the simulation, it has to assume a finite time interval. So blah, blah, just whatever. It's basically -4. That's where we started at, right? And notice the vertical intercept right here is at -4. So the initial position is the vertical intercept of the XT plot. Now, I know you're going to want to do this, so I want to stress something here. Look at this. There's a totally different set of rules for the YT graph. Just to be clear, the vertical intercept is initial position on the XT graph. Look at this. Down here, the vertical intercept on the VT would obviously be initial velocity. So there's a difference between what these things mean. There's a whole separate set of rules for the XT graph and the VT graph. The most common mistake on a quiz people make is they'll look at a graph and accidentally grab the wrong set of rules. Well, you're very lucky in that this class is online. You can have this page open during the quiz, and I don't care. So you can have it open and have these rules. There is no excuse for you guys using the wrong set of rules for the wrong graph or whatever. But every time you look at a graph, make sure you grab the right set of rules. I know that seems simple, but I've seen it for decades. Okay, decades. I've seen people screw that up. All right. What else do we have here? The slope. This is a big deal. The slope at any point on the XT graph is instantaneous velocity. What? Blah, blah, blah. Let's go look at that. Let's clear that out. Let's get in here. So look at this right here. Come on now. Let's go right here. The initial slope. So I could try and get rise over run and do a little calculation here. And it's hard to see, but I do want to point out that this value right here is the same thing as this slope. So the slope initially is +6. Now, wait a minute. Slope has units of rise over units of run, meters per second. Look at this. Okay, so if I did a calculation here, maybe the rise is, I don't know, let's do this. Slope is rise over run. I don't know the numbers exactly because I can't read them off the graph that well. We could try and zoom in, but I'm just going to fake it here. So let's say the run is 0.1 seconds. All right. The rise in this case might be 0.6 meters. And I'm just eyeballing that. Let me get my eraser out and clear this out. Okay, so I'm just trying to, maybe I could even make this bigger. Whatever, let's just draw it. The idea is right here. If I go over 0.1 seconds, I go up about half a meter, and that's where I'm getting these numbers right here. Well, when I do that, this is approximately equal to 6, and then notice the units work out, meters per second. So in a physics class, it's not enough to get rise over run. You got to do rise over run and get the units right. So in these graphing questions, it's extremely important that you always pay attention to the units on each axis. Are they meters? Are they centimeters? Are they millimeters? Are they nanometers? Right? Are they seconds, milliseconds, hours, days, lifetimes, whatever? Okay, so always pay attention to the units in a physics graph, okay? Why? Because the units affect the slopes units, and that will affect the answer you write in a computer question, and that may get you, that may make the difference between getting it right and getting it wrong. All right, let's go back here. Oh, sorry, just a second. All right, so concavity. So a concavity indicates how curvy it is, right? So there's a concave up. This would be concave down. And so in this case, this would be the acceleration is greater than 0. And this one would mean the acceleration is less than 0. A negative. Okay, so this is a positive number. This is a negative number. Let's go see if that holds true. In this case, aha, I see that down here, we had a -2 for our acceleration right there. That looks about -2. And notice acceleration on this plot is negative. We see concave down. So that makes sense. All right. Let's clear that out. Go back, see what else we got. Blah, blah, blah. Okay, these are just some things that you should know right here. If it's a linear graph, think about that. Linear means no concavity, right? So if you have a linear XT graph, you have constant velocity. That's just a fact you should know. Obviously, if it's a positive velocity, you'd have a positive slope. If it's a negative velocity, you'd have a negative slope. Let's go back here and look at ours and see what this means, right? Oops, oh, wrong one. right here, right? Look at this. I just want to point out the slope is not the same. The slope is changing, right? Sometimes the slope's positive, sometimes it's negative. Slope changes if you have a curvy XT graph. The slope changes. Well, remember, what does the slope relate to? Velocity. So if the slope is changing, that means V changes. If the velocity is changing, acceleration is not equal to 0. So that's supposed to be all related, right? If you have an XT graph, a position versus time graph, and the slope changes, what does that imply? That implies the velocity changes, which means acceleration is not 0, because acceleration is rate of change in velocity. All right. And look at it. Look at the velocity. I had a positive slope. I had a slightly smaller positive slope. Right at this point, there's no slope, right? Then we get a negative slope, more negative slope, even more negative slope. That's these points right here, right? As you get to larger and larger slopes, either plus or minus, that means different speeds. So this is a large positive slope, small positive slope, etc. Zero slope. Okay, so there's how those are all related. Let's go back here. And just so you know, a parabolic graph implies constant acceleration. So that's just a useful fact. And here's that. I'm going to say that's good on XT. Any questions about XT before I go on to VT?
What does a linear position graph mean for acceleration? Does that mean no acceleration?
Wait.
Like
what is, yeah. So you want to talk VT graph now?
No, for XT graphs, if
Mhm.
the like slope is constant, doesn't that mean that
this.
you'll have like a straight line on the V graph and then like no acceleration on the acceleration graph?
Yeah. So let's just do it.
Okay.
Right. So let me just -4. Let's say this is 2, or what did I say? 6? Yeah, 6. So when I run this one, that's what that one looks like. So if you had acceleration equal to 0, you get a linear graph, right? And then what if we go back here? Let's say it was -4, 6, and let's say the acceleration was positive, say 2. Let's run it. What do we get? Now it's going to be increasing faster and faster. It's kind of hard to see there. So let me reset that. Let's start out even. Let's start this one out at -10. And let's say the velocity starts out at 2. And let's say your acceleration is 2. So the idea here is we watch this one. You might be able to see it a little bit longer. It should start curving upwards, right? Oh, I hit sorry, I didn't hit 2 right. Now, here we go. Let me clear this out and run it back. All right. So now we're going to have this. We have a negative initial position. We have a positive velocity and a positive acceleration. You can kind of see it concave up now, right? So there's kind of some different cases you might imagine. Was that Edgar? Did I get your question there or no? Or was that Dom?
That was Dom.
Oh, my bad. Dom, did that answer your question? Okay, cool. All right. All right. So let's go check out the VT information. All right. Watch out. This is velocity is speed. We mentioned this already. That's the initial velocity. Now look at this. Remember, we already know that the value of V at any point is the slope of the XT graph at that same time. We've already talked about that, but just to be clear. So if you take the slope of the XT, you get the value of V at that point. So now what does the slope of a VT mean? So just beware, the slope of an XT graph gives you velocity. the slope of a VT graph gives you acceleration. All right. And so just going over here, let's go back. So I just want to point out here, in this case, this is +2. So if you want to, you could actually do the rise over run here. We start here. Let's say we go over 1 unit. How about 2 units? We go over 2 units. We go up 4, right? So that's 4 meters per second after 2 seconds, right? So what's the slope? Rise over run. So we get 4 meters per second divided by 2 seconds. Notice the units still work out. We get 2 meters per second squared. Now, obviously, you could get a negative slope and then you would have a negative acceleration. But I just want to point out that this actually works. You can kind of see it on the graph right here. So far, so good? Hope so.
Yeah. Would there ever be like a point where or how do you get it so your velocity graph curves?
You'd have to change the acceleration. And
Okay.
that is right now, that's kind of beyond the scope of our course. I could show you that later. It's not that that doesn't happen all the time, but we need to just understand we're all this chapter, we're pretty much doing constant acceleration problems. Now, what you could do is something like this, right? You could say this is 4, you could say this is 0, and you could clear this out, and you could run this one. Just give me a second. All right, and then you could go over here and change this one, whoops, to -2 and run it. And then you could go over here and change it to -4 and run it. And so, you know, this is kind of, you see how the velocity graph is starting to look kind of curved?
Oh yeah, I think I've seen some kinematic graphs like that look like that for acceleration. They look like weird.
Yeah.
Like that.
And I mean, I could show you those later. I usually do that in physics 161. All right. So non-constant acceleration, we're going to handle in 161. But that gives you an idea. This isn't a perfect idea, but you can see it kind of looks curvy, and there you go. The
Okay.
acceleration would have to be changing.
Okay.
Yeah. I mean, there's so many examples of this in the real world. Driving a car. When you hit the gas, just because you put the pedal at a certain spot doesn't mean the car's acceleration is constant. Right? Or when you're pedaling on a bike, right? Maybe you have a big burst of acceleration or maybe not right at the beginning, or running in track, right? If you're running, well, you get tired and your acceleration changes. So the real world is filled with those. We got to learn the basics. So we're going to keep to constant acceleration for a while. Okay. Yeah, good stuff. All right. This is a big one. This is kind of the last little piece here. Well, 2 things. One, let's say, I think that was Dom talking. So what Dom just said, if you have a linear VT graph, that means constant acceleration. Most of our VT graphs are going to be constant acceleration, or at least be able to split up into sections of constant acceleration. Not always, but most of them. And then here we go. What about the area under a VT curve? What does that mean? So remember, look up here. Area under the XT, that's not a useful quantity for us. Area under a curve does mean something. It's displacement. So let's go back to there and look at it. This is the toughest one for people. Let's get this out of the way. This is too complicated. Let's start with -4, 6, whoops, 6. And then I think we did -2. And I'm going to run this one. This is kind of what we started with, right? All right, close enough. So now in this case, what did we just say? It says the area under the curve, just to remind you, so we got this, area under the curve. Let's go look at that one. Whoops, right there. So where's my tools? Oh, shoot, I'm not sharing screen, am I? Sorry. My bad. There we go. Okay, so just kind of, let's look at this one. We're looking at this scenario right here. He's moving, he's moving, he's moving, coming back. I reset all the numbers. Sorry, it took me a second to get that back up. All right. So now the idea here is let's run this for a few seconds. How about 3 seconds? So 1 banana, 2 banana, 3 banana. Okay, it's not perfect, but I tried to stop it almost at the right spot. So look at this. What is the area that's been covered? Right here is the area. Trying to shade it in there. So I need to get that area. Well, this length to right there is 3 seconds, right? And what's the height? The height is 6 meters per second. And what is the area? Well, the area is the area of a triangle, agreed? Well, that's 1/2 base times height. Well, in this case, the base is 3 seconds. Got to keep those units. And then the height was 6 meters per second. Let's look at what happens to the units. In this case, the area, the seconds cancel. And I get, is that 9? I don't want to screw this up. I think that's 9 meters. Okay. What does that mean? It does not mean the person is at 9 meters. Look, they are not sitting out here at 9 meters. They started at, where did they start? -6 or did they, I've forgotten. Let's hold on. Just give me a second. Let's just play it back. Come on. Let's go back to the beginning. They started right here. So let me get that. They're starting right here at -4. And then we're going to play this thing and see if I could do this. So many buttons in Zoom. I'm going to slow it down so I can hit the pause at the right time. Moving forwards, moving forwards. There we go. So notice I got it right this time. I just want to point out this is the final position. The change in position, the displacement is 9 meters. Do you see that? So the area is the displacement. It is not the position. It is not the distance traveled. It relates to it. In this simple case, it happens to be the distance traveled. But watch this. All right, I'm going to keep playing this. And now from this point to the next 3 seconds, well, let's just do 2 seconds, say, or let's do 3, whatever. All right. And so in this case, now what's the deal? I'm looking at from right here to right there. How much time has passed? Just on that time interval.
3 seconds.
3 seconds. What's the height of this triangle down here?
-6 meters.
-6. It's weird. It's not. So we have a negative height now. So if I get the area and I plug in those numbers, I don't know if you could see this, but you're going to get -9 meters. And so we see that you went from this point to that point. Notice it's not 9 meters anymore. It's -9. So the area actually takes into account whether you're moving right or left. So if I did that, you could, whoops, not a J hat. You could think of this as having an I hat on it, right? It went -9 meters I hat or 9 meters negative I hat. So moral of the story, areas above the curve are positive, areas below, that's a negative. The area is less than 0. And here, this area is positive. Just like in a calculus class, which some of you might be taking, area is positive here. Now, I know we're running out of time. Let me just see if any of this made any sense. Let's do it this way. Let's do a quick summary here, right? To go from here to here, you take the slope, or if you're in calculus class, you take the derivative, right? to go from here to here, you take the slope. Now, if you want to go from here to here, you get the area under the curve. And again, if you're in calculus, slope means derivative, area means integral. And it turns out down here, if you really wanted to go from there to there, that would also be an area. So the same tricks that we did, and that's the only thing that there is to know about the acceleration graph. All right, so you take slopes to go downwards, you take areas to go upwards, keep track of positive or negative areas, keep track of positive or negative slopes, keep track of the units, and this will all be pretty straightforward. Yeah, that doesn't mean it's easy. You got to practice like crazy. In this case, the area is just the integral, and all it does is it relates to the, again, the area of the velocity gives you the change in position or displacement. That's the big one to know. And the area under the acceleration curve gives you the change in velocity. So let me just go to it right here. Here's your bullet points. Right here. Here's what the areas mean. And so that's, and then again, area of xt isn't a useful quantity. That's an introduction to these terms. We're running out of time here, so we probably don't have a lot of time to do a lot of questions. But I just want to point out where else, whoops. Get these off of here. I just brought this stuff up again. You can see that this is kind of the same stuff we mentioned before. If velocity and acceleration have the same sign, something is speeding up. If they have opposite signs, you're slowing down. And furthermore, velocity has velocity larger than 0. That means moving forward. So I just want to be clear about this. You should know that in a problem, a word problem, moving forwards and positive velocity are related. Okay. And then moving backwards and negative velocity, those two things are related as well. That's basically what you're supposed to get out of that. And so you could use that chart when you're getting started and you don't remember all this stuff. Okay. It's a lot of stuff to remember. Yes, acceleration graph is an AT graph. Yep. All right. So here we go. If you look at, oh my gosh, hey, it's only A through J. How bad could it be? 2.25 is probably a good one to do with the workbook open. And you should probably do this. I'm going to call class right now and call it after I mention this. But this would be a great problem to do before the next class period. I don't care if you do it today, tomorrow, or the next day. But yeah, you should do this problem and have the workbook open and follow the instructions and just use the solutions while you try and do this one. It's a complicated problem. Yeah, there's a lot of different questions. Everything that we just talked about is there. You've got some graphs. It looks a lot like what we just did. Only, I don't know if you could tell. Look at this XT graph. Is acceleration positive or negative from this XT graph? What do you think?
Positive.
Positive, concave up. And you could see it. So the idea is I gave you a set of graphs and you could compare the graphs. Obviously, look at this. You could, the idea here, for example, in part B, estimate the slope of this and then compare it to down here. So you could estimate the slope right here and compare it to this value right there and see if they're the same, right? And all right, that's cool. So that's the problem that you might want to do to catch up. Let's call that good. All right, so we'll pick up there next time. So make sure you do one problem and read the rest of chapter, whatever it is in the book, chapter 3 in the book, right? So chapter 2 in the workbook, chapter 3 in the textbook. Yeah. Any other questions? Jay, did you get any questions today or not really? Couple? Okay. You could definitely ask Jay lots of questions anytime you want. So, yeah, I'm going to stop the live stream now anyways, wherever that button is. Oh, I guess I hit this button.